Okay, so let's look at the formal definition. So an Euler circuit in a graph is a simple circuit containing every edge of that graph. So in particular, an Euler circuit is one that visits every edge or crosses every edge exactly once. And an Euler path is a simple path containing every edge of the graph. So more specifically, an Euler path is one that traverses every edge exactly once, going from one vertex to the other. And an Euler circuit traverses every edge exactly once, starting from one vertex and arriving back at that same vertex. So let's look at some examples. So within these three graphs, let's determine which contain Euler circuits, and of those that do not contain an Euler circuit, which contain an Euler path. So looking at this first graph, you may recall childhood games where you were asked to draw a figure without lifting your pen off the paper and without retracing your steps. And so you'll notice that shapes that you're able to do that are actually Euler circuits. So for example, in this first graph, notice that we can draw this graph without lifting our pen off the paper and without traversing our steps, right? So without crossing an edge more than once. Okay, so in this case, this is a graph that has an Euler circuit, and we could denote it by A, B, E, C, D, E, A. Of course, there are a number of other ways. We could start at any vertex and get an Euler circuit from that vertex, following the same kind of pattern. So notice that we simply traced outside. So we simply went through all of the outer edges. So if we try that with this graph, let's see what happens. So we can start from A again, go to B, go to C, go to D, return back to A. So right away that's a problem because we have returned back to A, but we haven't traversed all the edges. So far we don't have an Euler circuit. So we must travel all the edges, so now we need to go inside. If we go to E and then back to B, again we're in trouble because we've already traversed this edge. So we get stuck. If we start at A, go around the outside, and then try and go inside, we get stuck because we've already traced this step. So in order to be able to travel these edges, we need to either lift our pen off the paper or travel through one of the edges we've already gone through. So it appears that this graph here does not have an Euler circuit. It's also difficult, as we've just seen, to also get an Euler path. So starting at A, going on the outside, and then coming in, we still cannot travel all of the edges without traversing another edge. So it's also difficult. So we also can see that this does not have an Euler path, or we also guess that it also does not have an Euler path. What about graph 3? So let's try the same trick that worked for the first one. So we'll go around the outside. So start from A, retrace all of the outside. Okay, so we've gotten back to A, but still vertices or edges to travel. So far it doesn't have an Euler circuit. The last two edges we have to travel are on the inside. So notice we have been able to get an Euler path, but we don't get an Euler circuit because we can't arrive back at the vertex we started with. And no matter where we start and do this process, we can't get back to where we started from. So it doesn't have an Euler circuit, but it does have an Euler path, because if we start from somewhere, it is possible to visit all of the edges without having to lift our pen or retrace our steps. So this is examples of what an Euler circuit and an Euler path looks like, and in the next video we'll identify characteristics of a graph so that we can determine right away whether a graph has an Euler circuit or an Euler path. In this case, we haven't really considered all of our possibilities, so we don't know for sure that this doesn't have an Euler circuit nor an Euler path, and we don't know for sure that this doesn't have an Euler circuit either. But we'll be able to show in the next video that neither of these actually do.